compound. We will take what do you think? You take
Figure it out. Like, let's get one thing out of the way at a time. We're gonna all start crying.
So you said
We do 13 in class, we take home 14. Or we take both home and then you get a lesson. Can we have one to hold two home?
okay. So I think probably
Okay, I have a question. So can we like take one week before? Because I feel like it'll be really stressful going forward.
I think that's a good idea. Take 14 home because 14 we just study, and we'll do the travel 13 tomorrow. Later 13, not that difficult. Right, so I'm going to study the organometallic compound. And what is the characteristic of organometallic compound is you will have the bond between some of the metal and carbon. So let's make sure that it's clear. We saw some of those compounds before, for example, sodium methoxide or sodium ethoxide. Those kind of compounds, we don't call them organometallic compound. Even though they have metal in it, but the bond between sodium and oxygen. So we have to think about those bonds have to be between metal and carbon. Okay. So these will be the main compounds you are going to study in this chapter 14. In addition to this type of compound, and we also study a little bit of some of those when the alkyl, maybe benzene, maybe something like methyl or ethyl, bonding to like some other atom, not the carbon, not the oxygen, phosphorus. So some of those compounds is very, very useful catalysts. But most of the compounds you study in this chapter is carbon has some bond with some of the metals. First, the nomenclature. And so briefly you will see the nomenclature. Yeah.
Sorry, before we go on, I noticed in the notes for 12 yesterday it wasn't posted. So can I listen to this or do I have to take notes? I just have to pick one.
And yeah, so I would say you need the lecture is very important, and so you can have a good lecture. And if you don't want to do the lecture notes, yesterday I tried to post like the version I use for the lecture notes on the yeah.
Okay, because last night it wasn't on.
I probably. I suppose to put the chapter 12. What I did is chapter 9, chapter 10, chapter 11. I wrote these 3 chapters. So yeah, that's. I did not do the chapter 12. I thought.
Because I missed so much of 12, but we went very fast at the end. So it'd be really nice if you could put those up like the day after, like after we left.
After we left.
Yeah.
Probably before, not before. I will just, I will put both version, and the version you have right now, just the small version with the blank. So in that way you can print out and bring to the class and do as much as possible. And then I will put this version on the blackboard. Then if you miss something, then you go back and can just read it. So I will put 2 versions. This one I will put like for all the chapters. Then I will still keep that simple version with the blank also there.
So that way I can listen and not be so busy writing instead of.
Yeah. Initially I thought probably you you listen carefully, you write, and you use all your 5 senses.
Taste. It's just hard, like in a 5-week class, like some of my senses die.
Some people.
Some people what?
Let's see, for the main group method, you will name as a substituted derivative of the method. What that means is your name will end with some metal name. For example, one here we say that one is cyclopropyl lithium, and one here sodium. So name ending with sodium, right? And diethyl magnesium. And then you can treat the substituents other than carbon as anion, right? Which means you see some part of the name is still same as the part on the top for this C3 MPI. You still name the first part methyl magnesium, right? But you still name the I, so therefore you name that methyl magnesium iodide. Right? Similar for this one. So this one you name that diethyl aluminum chloride. So A and B have some of those similarities. So A and B are similar, right? So these two are similar. You pretty much start with some of those alkyl, and kind of your metal name is the ending. In A, yes, your metal name is just the ending of the full name. For the second part, B, these two examples in B, because you have another atom, you put the first two together, name that as a cation. So therefore, you call the methyl magnesium is kind of a cation, and your I is named that as an anion. So it's very similar as you name those ionic compounds. So then for the transition metals, you will kind of do the opposite. But the opposite makes sense because for the transition metals, those transition metals actually you can think about, so for example, the copper. The copper together with the dimethyl is actually carry some of those negative charge. Now in the general chemistry, we know the negative charge ion is ID or ATE. So therefore, in those kind of compound, you name the transition metal, not the metal name. You will find the metal like the root, and you use ATE. So the first example you see, you see that become lithium dimethyl cuprate. So lithium name as cation. And then this the methyl, the C3 together with the copper is named as dimethyl cuprate. Very similar as you have carbonate or sulfate. Right? Some of those exceptions. One exception, for example, is acetylide. Acetylide ion, that means you have a C triple bond to C, and then one C has an H. The other C has a lone pair negative ion. You can name this as sodium acetylide. So acetylide really referring to, you saw that before in chapter 9. Acetylide is a C triple bond C like that, and negative.
Isn't there another H on that middle?
Yeah, that's acetylene. So acetylene. Remember we have those H and C triple bond C and H like this. So this is a acetylene, right? You can change that into that by using some of the strong base. I think the first lecture we know the strong one of the strong base is Na H2. So once you have that happens, so then this suspected ion can bond to this. Okay? And then so this guy and this guy is separate, but this is ionic. Okay? And then this guy become the conjugate acid, the NH3. Okay? So the naming, briefly we will just talk about like that, and when you have time, just read the book carefully, do a few more practice. And obviously on the quiz or on the exam, there may be a few questions about naming. Organic tool, most of the organic tool is objective is about the reactions and mechanism. Spectroscopy is a lot of classes, they also cover a lot of the spectroscopy, so that's also important. And you already studied that in the Organ 1. Okay, now, because you change the bond of carbon, and usually carbon bonding to H, bonding to carbon, bonding to halogens, okay? Now you change to metal. Okay? Metal is less electronegative. All the metal is less electronegative if you examine the table. All the metal. Okay? The most electronegative metal is gold. The gold, Au 2.4, and the carbon 2.5. So therefore, your carbon becomes more electronegative than all the metal. That means the carbon can withdraw the electron from the metal. Sometimes we write those structures as ionic, even though they are not that pure ionic. According to the definition, ionic you have to have the difference about 1.6 or 1.7. So sometimes it can be very close. So now you see here is a total kind of a Gilman switch. So before you have that carbon with X, carbon is kind of have those cation characteristics. Okay? So it can be attacked by some of those nucleophiles. Okay? Nucleophiles like some of those negative charge and maybe azide, maybe methoxide. And it can come in and attach the carbon, Okay? Now, if you switch the partner and you have the carbon bonding to some metals, carbon has more electrons. Okay? Now, carbon, instead of attacked by the nucleophile, carbon itself can act as a nucleophile. So carbon just carry the negative charge and attack some guy with some of the positive charge. And so therefore in this chapter we will learn how to make some of those compounds and how to use them, some of those very, very useful compounds. Okay? So let's see first how to prepare the organolithium and greener reagent. Organomagnesium is also known as the greener reagent, and we have a lab. So we will take some of those vanadium bromide, and we will put that in a diethyl ether, and then we put some of those magnesium, and then we heat that out for like a few minutes, maybe like 30 minutes and 40 minutes, and then we will produce the greener. So in general, you can produce this greener or the organolithium compound by taking the alkyl halide and primary, tertiary, or even aryl, like I said, the vanadium bromide, even like a vanilla halide. You can see here the general reaction. You take the halide, the X means halogens, reacting with lithium. Then you see the lithium bound to the R, and can take pretty much any kind of halide. That halide, in this example, you have a tributyl halide, a tertiary halide, and you produce that organolithium. Now this organolithium, well, we taught the different compounds than we saw before. Right? That means this carbon has a lot of electrons. It's the sort of the carbon nucleophile. Carbon nucleophile is very unique because you can use that and take some of those carbon cations and you will produce carbon-carbon bond. The last example is you take benzene, bromobenzene or benzyl bromide plus magnesium diazoethyl and you produce the green yarn.
So why is this the halogen?
Why? Very good question. This time the halogen doesn't go away because the magnesium. Okay? Magnesium, remember the group 2A, right? It can lose electrons, so somehow lose electrons to carbon, but it still can lose electrons to Br. You need to lose 2 electrons to this field. Right? And that's yeah, the temperature will bring some rule. If you want the Br to go away, you are adding another phenol here. Okay? You will have a diphenyl magnesium. That probably less 0 than the structure you have right now. Therefore, you just have you just have like one magnesium bonding on one side of benzene, the other side still has Br. You want the Br goes away, you might think about this structure. Because magnesium, obviously, you want magnesium in your structure, and magnesium wants to lose 2 electrons. We did not see that happen. Right? We did not see that happen for this reaction and this condition. If you have Mg like that, have 2 phenol, is less stable because you still have a lot of electron on magnesium. That's a very good thing too. But we find out like Grignard initially, with the Grignard, he found out just use magnesium. You can try use beryllium, use calcium. And you're probably not that efficient because it depends on the electronegativity. All in the same group, they have 2 valence electrons, right? And well, depend on if it's 2 electron negative. You not lost the electrons very easily. They just keep the electron on themselves, right? If you lost the electron too easy, and then your bond probably becomes weak. So this problem 14.2 is you want to write equations show how you prepare 2 methyl group pure magnesium bromide, the structure gives like that, from 2 methyl propene and some other materials. Right. So you do the ratio synthetic process. This material you want to prepare. Right? And you want to prepare this from that. So what do? You see, you can get this one from this. But this will be 2 steps. We're getting this from that. Let's think about how can you adding a BR on the side, not in the middle. If you have this, if you add HBr, and you will produce the carbon cation in the median, the BR will go in the middle. Right? But the BR is on the side. So after you analysis, you identify you want to produce this compound called the 2-methyl, right? And the group here magnesium bromide, so this one. And it gives you this, and you want to produce from this 2-methyl protein to this 2-methyl protein. So what do we say? What do we do is first free radical halogenation on this alkene. So I add the Br on this on like this primary carbon site. That's kind of very unique for the free radical. And once you have those halide, no matter what halide, you might have a tertiary halide, orbital halide, aromatic halide, or vanilla halide, and you can just use magnesium and diethyl ether. If you read the book, you will see you use diethyl ether, that will make those your magnesium metal and your product more soluble in your solvent. Some of those coordination. Any questions? Then the order of halide reactivity is I will be the best one. If you have some of those here, instead of BR or I, your reaction will be more complete. Your yield will be high. Then BR, then CL, then F. So when we do the lab, when we do the green on the lab, we have what we have is in the lab. What we have is there's a bromo benzene. We also have those I2 crystal solid or whatever in the bottle. So what we did last year is some group take the bromo benzene and also adding a few drop of those I2 crystal, and then you shake it. Then you add the magnesium, and then you use diethyl ether and then heat, and then we produce the green gas, and then we produce, and we add the dry ice CO2, and then we produce the benzoic acid. The other group don't use that. They simply take the bromo benzene with magnesium with the same reagents. The yield you can see is much low. We don't have too much of those crystal finally produced. So when you do the lab, if you see the iodide and the crystal and add on to your bromo benzene, your reagent will be much easier. That's because those reactivity, the I halide is much reactive than the BR and CL. You can even use vanilla chloride, power bond to CL, and can also produce the green yard. So those are the sort of the polar aprotic solvent. You have to use those aprotic solvent. The aprotic solvent, that means your pKa for those solvents. If you have H, you still have H on it, for those pKa for those solvents should be higher than the pKa of our compound here. Should be comparable. You see here. You see this guy the pKa. If this carbon here is sp3, it will be about 62. Right? If this carbon here is sp2, you probably get about 45. So you want to have the solvent, the pKa, at least higher than 45. But if 45 is not good for those guys with sp3. sp3 that can even gravity electron the proton away from that. For example, if you want to prepare the grignard and you have that metal simplified that version, the grignard. Once you have the grignard, this one maybe magnesium, maybe the lithium, just organometallic compound, and this bond here is positive, so this is plus, this is negative. Then this negative can attack the proton if you use alcohol. Obviously, the alcohol H can be grabbed away. Then you are not produce like what you're supposed to produce, and you are change those halide you're starting from into your those hydrocarbons. But you can use this kind of property and prepare those like the triple bond organolithium or the grignard. Okay? So if you have the carbon like triple bond and you want to add magnesium and Br here, you cannot simply take this guy somehow change, or this guy has does he have a Br here? You probably can produce triple bond have a Br here by using remember we prepare the triple bond by elimination, substitution. Okay? You can start with not triple bond. You can start with this Cl. So then here maybe 3H like that, and you can use a very strong base like a sodium amide. Remember what we did called elimination? Eliminating like 2 of those Cl, you still have 1 Cl left over. So you can produce something like this. Right? So those kind of alkyne halide. And then you think, okay, if I have this alkyne halide, I will just add on magnesium and I use diethyl ether. I will try to produce this guy. Okay? But they said you cannot produce in that way because the magnesium of produces grignard is like those single electron transfer and proton transfer process. Now we know like when you have a triple bond, you can reduce the triple bond by angling in ammonia or the grignard catalyst PP with A2. Or they simply A2, a lot of A2 process, palladium, platinum, nickel. So if you take this type of alkyne halide and put a magnesium in, the reaction will not happen to this one. Okay? But you can use the very, very strong basic property of those grignard or organolithium and prepare those kinds of grignard. So usually this grignard will come from the halide. You take some halide, methyl bromide or acyl bromide and put a magnesium and you produce this. Okay. Now produce this kind of grignard is kind of you move from grignard to to bromide. You cannot go from halide to bromide. So here this way is not possible. But you use another bromide, you can produce this bromide. Right, so this is about how you prepare those bromide. Now here's the reason. So those are magnesium, and you use the halide and put those metal loss in electron very easy. Right? So the metal loss in electron very easy. Your first step is you can see in the prepare of the organolithium compound. The first step you start with the halide. You put some of the lithium metal in it. You finally produce your metal lithium. Right? So you first step you just adding one electron and produce this radical anion here. So you have a radical anion, which means you have one active electron. Actually you have two active electrons. So you have negative charge, you have electron. So you take chloride away. So you take chloride negative Cr away. You have this radical. And then that radical combined with another lithium atom, you finally produce your organolithium. You see this process is a single electron transfer and a single electron transfer. Whenever we have those active metals, and you will see the electron transfer, one electron transfer at one time. That means that can also happen on a triple bond. And that is the reduction process, one reduction process of triple bond. So this second step is very similar. You start with this halide, and so then this magnesium have two valence electrons. So magnesium have two like those electrons. You use one electron at one time, produce this radical anion first. So then this radical anion obviously is not stable, right? And you can dissociate or break this apart. I think it kind of makes sense it happen like in this way, right? So here you pretty much have a negative charge and one electron. You break apart into two parts, and one has negative charge, the other one has a single electron. So which one should have the negative charge? Which one has a single electron? The process will tell you the chlorine has the negative charge, the carbon has the single electron. So that even more stable because you imagine you do the opposite. You let the carbon have the negative charge, the chlorine has the single electron. And we know chlorine is more electron negative. So that the chlorine has more electron, has a negative charge, that become more stable. It's more like more stable, that means your reaction will happen faster. then they will come together like that. You will take the magnesium 1 plus, and that can still somehow donating 1 electron. It will donating 1 electron to the carbon, because carbon only have 1 electron. So there's a bond between carbon and magnesium, and in the same time, because magnesium appears as a positive, so you need the counter ion there. Right. So what is important is that when you have those organometallic compound, the carbon is relatively negative. Right. And you can use this to prepare some compound. One example of compound you can prepare is those alcohol. Let's see the first example of making alcohol is using the organolithium or Grignard react with aldehyde and ketones. We will study the aldehyde ketones in chapter 17 more details. So this is how this this organic chemistry textbook organized. There's a lot of those intersections or overlap, somehow overlap. Right? So in this chapter you study the aldehyde, and then later on you will study more aldehydes. So we'll kind of review later on when we study that and review this reaction. Aldehyde or ketone have those carbonyl. Carbonyl is a carbon double bond to the O. Right? So usually I think in the lab I briefly talk about the structure of carbonyl. So carbonyl has carbon double bond to the O, and the oxygen has relatively small amount of negative charge. The carbon has a positive charge. The carbon in the carbonyl become the electrophile, looking for electrons because that is positive. Now you just produce those Grignard and organolithium. So in Grignard organolithium, the carbon that's bonding to those metals relatively negative. And naturally, those reactions will happen. Okay. For example, you take the formaldehyde. Formaldehyde there, okay. So the reactants, if you rewrite, is RMGX. Okay. Then you plus this formaldehyde, you write that out, you have a 2H and a carbonyl. Okay. So that we said the carbonyl is a functional group, so this oxygen relatively negative. The carbon here, relatively positive. Okay. Our organometallic compound, so here we have some carbon, so some carbon here, relatively negative. Okay. Your magnesium, relatively positive. Okay. And naturally, so this is negative with electron, it will attack the carbonyl carbon. Okay. And initially you have electron here, and we'll push the electron out to the oxygen. You will produce an intermediate. So intermediate will be something like this. Okay. And then you have those special ions like that. So this ion is this ion has negative charge on the oxygen, and you can take some of those protons from some of those solvent, for example, acid or water, and so this one finally plus H plus and produces alcohols. position R switch. This doesn't matter. It's tetrahedral geometry. You can rotate. If I write R here, it's same as you write R there. So this is for location, doesn't matter where. For this example, doesn't matter what you write. If you want to see the chiral center, if you see the chiral center, if I draw this is where that you don't switch them simply like that. So here I did not emphasize the stereochemistry. Okay, so this alcohol, if you take a formaldehyde with organolithium or those grignard, you produce a sort of primary. What you see is you adding one more carbon on your in vitro alkyl, that in the alkyl halide, which becomes either organolithium or the grignard. Okay, so again, you're starting from organolithium. The organolithium actually is starting from those halide. You can produce a secondary alcohol by using other aldehyde, not the formaldehyde. Formaldehyde have only one carbon. Okay? If you see this example, you have this formaldehyde, one carbon, 2H, 1 O. You produce an alcohol that has one more carbon than your starting carbon chain. Your starting carbon chain only is cyclohexenol. Okay? Now you have this alcohol has one more carbon on the side of the cyclohexene. And that alcohol is still primary. That is the primary. The OH bonding to the carbon, then the carbon will bond to one more carbon, so that is primary. If you use regularly aldehyde, which means you don't have 2H, only have 1H on your carbonyl, and you produce the so-called secondary alcohol. You can see a lot of examples. I think in the next notes is the example. You can just come up with any example, like some of those grignard. Grignard, for example, a simple grignard, Mg, like that. And I will take the simplest aldehyde that is not a formaldehyde. It's acetylenic like that. What you see you will produce is an alcohol like that. Yeah, I skip it. So those are the intermediate. Yeah. So if you want to write, you will see just your first step, adding that. Second step, you adding some of those waters. Okay. First in diazo ether. Very good. Diazo ether like that. And you have to clearly indicating you have two steps. Okay? You don't put them together. If you put them together, what happens? You are lost the grignard. Okay? So the grignard were reacting with water or acid become the hydrocarbons. And you see the example here. I said you can come up with many examples. The example here is usually like that example Nancy. Still grignard, and you have this acetylenic. So next, the simplest aldehyde, the simplest one is formaldehyde. This have only one H, and you take that tag, you produce the intermediate, and you work up, you produce a secondary, and then you compare this secondary alcohol with the initial your grignard. You have two more carbon. So now you can guess how can you prepare a tertiary alcohol from this kind of approach. how can you prepare a tertiary? This one is a secondary because you still have H here. Right? And that H is from this H. So therefore, when you want to produce a tertiary alcohol from the Grignard or the organolithium, you will use Grignard with what? With ketone. Okay? But this second thing is about you use Grignard with aldehyde or ketone. Okay? Two-step process produce alcohol. Okay, so the last example here, so this guy is a tertiary alcohol. What you use is a ketone. In this example is a cyclopentene. You can take some other ketones. Simple one, let's take the acetone. And you want to make some of those, let's see, like that. And two-step, write one in like the diethyl ether. You say two, you add acid, and you finally get something like that. So you get a weight here. Then you're adding this group right here. And this is also a tertiary alcohol. In the example we saw, like in the three examples, we can replace the Grignard by the organolithium. Okay? That's one example. You take that aldehyde and you do two-step process. One step you add in that organolithium and in the diethyl ether. The second step you use acid. You see the change. Okay? So this aldehyde and this organolithium together make a secondary alcohol. Your carbon chain adding together.
It's the structure that you, what is the,
Which carbon from which, right?
yeah, the aldehyde, like in the middle, why is there that, is there two solvents?
The aldehyde in the middle of the
Is the
two.
first step, like,
Oh, this one?
yeah.
Yeah, this is the solvent just for the top one. So for the
So
first step.
there's two steps.
Two steps. Two steps. Two solvent. Yeah. Two steps, two solvent. So the first step, you add in the organolithium, you use diethyl ether solvent. Okay? Second step, H2O plus the solvent is just H2O. So let's clarify your first step. Sure, write out something like Li here, and in the diethyl ether. Okay? Then you'll see your second step is some of those acid in H2O. So then we produce this alcohol. And this alcohol altogether has 8 carbon. Okay? But this 4 carbon is from that aldehyde. And this 4 carbon from our organometallic organolithium, you get the same products as you use green. Again, here we use two steps. Here you use organolithium, the same organolithium, but add on to a ketone. You pretty much get the same started there. But here you have this is a metal. If this is metal, so this alcohol is tertiary. The magnesium you already saw that before. It's just very similar, like a two-step magnesium. First step, depending on what you use. If you use green yarn or you use organolithium, very similar. So you use green yarn, the electron from the RMG bond. You can think about that is the negative charge on the carbon on the R, or you can think about it like this. Carbon needle, yeah. So that picture give us small. Let me just write that up, and you can see the more clear. This is our green yarn. This is our green yarn. So what happened is these two electrons from this bond come attack this carbon. Then these electrons will flow on to oxygen. So this will give you oxygen. 1, 2, 3, 3 pairs, negative, and carbon, and this two metal, and then you have this R. The R comes from the green yarn. You still want to keep the suspected ions. So the suspected ion, you usually will write them close. You still have the Mg and Br. It doesn't matter if you show, like, if you want to write this magnesium, you don't have to show this plus and negative clearly like that. As long as you show how you adding this R onto this carbon, and you just write this O and Br together, and that'll be good. Okay, so now we know this is a base, right? So base, if you have some of those proton, whatever, maybe from water is very comparable. If you take it from water, you will get hydroxide. Hydroxide is very comparable to this. You probably add a little more acid to make the reaction finish very easier. So that is the second step, right? The second step, I said, on the test or exams, I will tell you step 1 is a nucleophilic attack. Nucleophilic attack, that means you need a nucleophile. Nucleophile has those negative charge. Then you will see the negative charge is going to attack what part of your molecule. And you're looking for the part that is positive charge. Right? And then I will tell you protonation. Protonation, that means you're going to add in the H+. And then you're looking for where is the base, where is the negative, usually negative oxygen, okay? Or some of those negative carbon. Pathogens. We know this practice predicting the product. What do you think that will happen? What is the product? We have benzaldehyde, right? And we have carbon here. what happens is this, add on that, add on the carbon, carbon, carbon. I will skip the intermediate, and you produce this kind of alcohol. If you want to write out the intermediate, just write the intermediate is this O and Li cross. Then you protonate. So I know write that O negative, but it's the same as you just. Yeah, so because here we don't have those stereochemistry, and you can write this double bond this way, that way. We don't have cis trans problems. Right. I think that's a good point. You make sure you remember this two-step process. So the first step must introduce aprotic solvent, then the second step you doing kind of like a workout. Okay, now breathing is this one, right? So we have now this time we have a ketone and a Grignard. Ketone and Grignard. Usually you will probably keep the first reagent carbon chain, and that initial carbonyl become hydroxyl, become alcohol. Okay? Now you are adding the other carbon chain. The other carbon chain has 3 carbons. 1, 2, and 3. You add here because this carbon, as initially you have this structure, so this is our ketone, right? And this has negative charge, and this carbon here, the carbon here, even the carbonyl has a positive charge. Okay? If you want to memorize it a little easier, you can take this. So you can imagine this Grignard as written right now. You have a bond with an Mg and Br. If you want to prefer, you can think about this as this. The negative here, and then you have Mg Br plus, right? Now you can see clear that this negative ion is very good nucleophile, right? And it was looking for some place and more plus, more positive. Right? So it was looking for a place that carbon. Because arsenate is more electronegative. So this arsenate is more electronegative. The carbon, because the arsenate is more electronegative, get put the electron away from the carbon, right? Or you can think about this resonance. Okay? So even though that resonance contribution is not that important, carbonyl will have those resonance. Probably from the resonance you will see that if you really see the plus and negative attack, you can think about the carbonyl resonance. So we have this 3 carbon electron resonance. So you put the electron up, and you will produce and negative. Now here will be plus. So the resonance, even though this will be the major and minor, actually those kind of resonance, and later on in chapter 20 you will study those are super the enolate. For for now, you just think about this carbonyl carbon. It's kind of the polar bond, and we study in general chemistry. Polar bond, one part is plus, the other part is negative. Okay? So the carbon is plus, and ours is negative. So those structures are similar. You have 2 carbon here, so 2 carbon here, and have 3 carbon here, 3 carbon here, 1 carbon there. Again, I did not emphasize those stereochemistry, so you don't have to worry about where you write those. If we this guy, this center here is the chiral. Okay? So we create. Okay? We create. So this is a chiral carbon now. We have a chiral carbon. You start with a chiral. So before the reagent, this component is a chiral, that component is a chiral, and you don't have any chiral reagent or catalyst in the process. What you produce is you will produce sort of the racemic mixture. So you will have 50% R configuration, you will have 50% S configuration. So this reagent is the kind of reagent you can use like in the lab. One lab we do similar. So what you do, even though it's not that exactly the same. Okay. Now here you will see you identify what you can get. What we use is the Grignard, and then here is what? The formaldehyde. So you will get a primary alcohol. Let me just draw here the similar orientation. Okay. So this is O, and this is C3. This right similar. This become O and H. So this is a primary alcohol. Now note, the addition of Grignard and organolithium reagent to aldehyde or ketone to produce alcohol is the most frequently used method because 2 reasons. You make the compound more complicated, you have like more carbons. And another reason is you get alcohol. Alcohol is a very good kind of functional group where you can change into many different things. Right? You can change alcohol into halide. Then you can, even before you change, you can dehydration. Then you can change that into the alkane double bond. Then you have double bond. You can change the triple bond. You have all those reactions. And now the second reaction of those Grignard or organolithium is you take those organolithium or Grignard reacting with some of those acetylide anion. Acetylide anion, which means you have anion on the triple bond carbon. Okay. And now kind of quick review. Okay. How do you prepare those acetylide anion? acetylene anion is the structure. So this is the so-called acetylene anion. Acetylene anion is anion, so most of anion are good nucleophile. Right? So you can use this as a nucleophile, nucleophilic addition onto the aldehyde or ketones, and you can imagine you will produce alcohol, which is sort of the acetylenic alcohol. The acetylenic alcohol is those structures. Okay, so here some other part. But at least you know you will have a triple bond, and you have a bond into a carbon that has OH. And we know how to produce this guy. In Chapter 9, we use this guy, reacting with some of those halides, and make more triple bond, make longer molecule with a triple bond. And now here, you prepare this, then you can use this as a nucleophile, add on some of those aldehyde or ketone. Okay? For example, you take a very simple ketone acetone. Okay? You take a simple ketone acetone, and two steps. One step in that diethyl ether. Second step, H3O acid, and we will produce R triple bond C, and like that. Another example, you take this sodium acetylide, reacting with that ketone, okay? And you will produce another tertiary alcohol. And this kind of tertiary alcohol has a special name because you have this acetylide part, the triple bond. Any questions? Okay. One example, so this example is you take this formaldehyde, so there was adding one more carbon on your initial chain. Your initial chain has this triple bond and the end. Okay? Now this has one more carbon, and you produce what the primary alcohol. Okay? So now this example here is a little different than what we saw before. What we saw before is like using that kind of sodium acetylide, and here we use the Grignard type of alkyne, triple bond with MGBr. And now the question, how you produce this? How this one is produced? Usually when you produce a Grignard, usually the Grignard was produced by some of those with magnesium, right? To produce the energy gas. So this is how we prepare the usual grain yard. Now this grain yard is a little different because you have this empty bonding to the triple bond. And we talk about that briefly, how we prepare this kind of grain yard. Anyone remember how we prepare this kind of grain yard? As a user, as a user, okay. Okay, so you probably were starting with like those alkyne. Alkyne, you need possess a 6 carbon. So now we have one hexide. Okay. You cannot take this guy. You cannot take this and just simply add Mg in like the bias of ether. So this approach does not happen like what you prepare. Okay? So what you do, you will take this one, take this one, and use this. For example, you can use a simple one like that azure magnesium bromide. So you use a grain yard to produce another grain yard. So that will prepare the PRMG. And now you will have this grain yard. Plus, the initial grain yard becomes simply like that. That just become acid. So we just write out CS3 and CS3. So that's usually that's not the usual way you prepare this kind of grain yard. Use writing as following. I mean, use similar. You don't use it. If you want to prepare that triple bond with 6 carbon, and this example is just like 2 carbons. Okay. Any question? Use ratio synthetic analysis to develop a synthesis of 2-phenyl, 2-butanol from benzene and 2-butane. Now let's see what is our structure for the compound for the product. 2-phenyl, 2-butanol. So you have and then you have the OH. Now you want to produce this from 2-butane. Right there. Okay. So any idea how can we change this change this compound? And so you want to get this one from this. And the price range. You do a ratio synthetic analysis. So this chapter we talk about how to prepare alcohol from grain yard and aldehyde or ketones. So So something happen in this on this carbon, because this carbon has a weight. You do a few like those phosphor line bond cutting. You see, if I cut in here, that means I need this kind of. I already have a ketone or magnesium. But basically, you want to do like a carbon bond cutting into this kind of fragment, which means you want to have a benzene and you want to have a 4-carbon chain. So therefore, the best way to cut in this molecule is to cut in here. So then you will think about, so you use, so you cut that apart, you get the benzene, and you have that apart. So you see, reaching synthetic analysis, so this guy can prepare from the brainyard on the benzene, so we're right from that, plus from a ketone similar like that. Then you just do a few more steps. You see, this guy can get from benzene, this guy can get from this. Now just review, how can you get a ketone from a triple bond? One very simple step. You can get a ketone from a triple bond by doing what? Hydration. So you just simply add H2SO4 and some of those water, and maybe use the cool enzyme HgSO4. That will become ketone, right? And how you make a brainyard take our step. So how can you make a brainyard from benzene? You want to make a benzene from the brainyard. You can make a brainyard from benzene. What do we do? Okay, now think about how we usually make a brainyard. Usually a brainyard you make from what to what? You need, so let's say this guy, MgBr, to reach synthetic, that means you need some of those, usually Br, because Br is easy to work with and it's not that expensive, right? And plus Mg. Now how can you get the Br bromobenzene from benzene? Benzene, how can you change benzene into bromobenzene? Chapter 12. You use addition the Br2, the catalyst is Fe Br3. Right. So now you have, once you have all those few steps, then you will see you just going forward. See what we did here, not that easy to see properly. So you take a benzene with Br2, Fe Br3 produce bromobenzene, and magnesium ether produce brainyard. And here you will simply take the H2O and acid catalyst ketone. Then two steps. Nucleophilic addition of the brainyard work out. Any questions?
Break time.
Good. 5-minute break. Take a 5-minute break.
Sounds the best one I want to listen to.
Yeah, it's good.
There's also a question.
Yeah, it's like straight up. Look around here, people like that done.
That's what he was telling me right now. He's like, double school. Midwestern is hot. I just wherever I get it is where I find it out. I was going to go to Chapter, but it's like 2 hours from now. I just do it.
No, Tiger, Tiger, would you guys
Wherever I
want
get it.
to
But like Cali's expensive. I feel that's just a lot of money.
Okay, so let's continue on the Chapter 14. Chapter 14 is about organometallic compound. So far we studied 2 metals, one is lithium, the other one is magnesium. And this section is about those organo-zinc reagents. So zinc usually also produce 2+ ion. So therefore, it seems like similar as magnesium. You can start with aryl halide plus zinc. By ethyl ether, you produce R zinc X, right? So then you produce that reagent. That reagent is not so reactive as our Grignard. Compare with our Grignard, so if your Grignard is R MgX. And then you see compare those electronegativity and the electronegativity for the zinc and magnesium is much different. Zinc is much more electronegative than magnesium. Magnesium, the En for Mg equals 1.2. The En for zinc is 1.6. So because the electronegativity difference and zinc is more electronegative, so the bond between the R and zinc and X is less polar. So therefore, your carbon don't have that much of Chapter-14. And so usually those zinc, organozinc reagents not very reactive on the aldehyde or the ketones. Then these two scientists, the Simmons-Smith reaction. So they use kind of one spectral, those halide, dihalide, diidomethane C2I2, and treat that with zinc. And you get this isomethyl zinc iodide. You still have 2 I in it, and you have a C2 and a zinc. Okay. You can see this reaction is very interesting. It can change a double bond into a cyclic propane, into a 3-member circle structure. And because you produce a ring structure, and you are thinking about those cis-trans isomers, so this reaction is Simmons-Smith reaction is region specific. If you start with trans, or if you start with trans or cis alkanes, or probably E or Z alkanes, and you will get those. If you start with a Z alkane, Z double bond, you will produce a cis, those cyclo propanes. If you have a E double bond, and you have a trans product. So this reaction, the Simmons-Smith reaction, you can just, you don't have to write this kind of intermediate. You produce this guy from the reaction of diidomethane plus zinc. You can just simply specify, you take those kind of alkane, okay? Maybe they are cis or trans. Let's say I take this one, and you just you add in like a C2 and I2, and you see like in zinc and copper and diethyl ether. Alright, you don't have to like do it right now. Then you take this few reagent and produce that IC2 and zinc I. You don't have to write that product. You have to take those reagents, and remember this reaction, the so-called stereo specific. It will keep your initial stereo arrangement in one of those reagents and produce what you produce. As you produce a ring structure, 3-member ring structure, and if it is cis alkanes or the Z alkanes, better probably just use wedge or dash, and I will use a wedge. Means here you have a CH3. Now this CH3 comes from here. This is CH3. Okay? Because you started from the Z to the CH3, and this methyl and ethyl on the same side, and your product will be on the same side. And you see some other examples. Two more examples. You sign here is E in E double bond on different side, and your reagent product has those trans chemistry, trans stereo. And this picture will see that if you see those kind of structures similar, so that tell you you are adding this one carbon on this double bond on one side. Yeah, so this stereo specific property you can see, it was kept by if you adding like those H on H, and you see the H in the structure. So here H here, this H here. Okay? So these two H here is actually on the same side of the double bond. So therefore they will be on the same side of the ring. Okay? So these two H here is actually these two H. So they are on the same side. So these are the so-called stereo specific properties. So this result of this reagent make us think about the. So this guy, the so-called iodomethane zinc iodide is like an I, and C2 zinc I. From this few like combination, you add zinc and this, and from that CH2 and I2, you produce this, and you finally produce a structure like those kind of three-member ring. You're adding a three-member ring. You see the double bond disappear. You're adding a carbon, you produce three carbon ring. So this reminds us one other special reagent. We call them carbines. What is the carbine? You see the name carbine. That means you kind of have E and E. So the carbine looks like this. H2 carbon, 2 electrons. So instead of double bond, you have 2 electrons. That makes those kind of species very, very reactive. So usually you can produce a carbine from some special reagents. For example, this diazomethane, which has the formula C2I2, and you can produce, you take that one, and you use light or heat, you will produce something like that. But this kind of intermediate, very difficult to isolate, but it's very reactive. It will it can react unselectively with any H, any carbon in your molecule. They just take your electron away from those H or carbons. Right? Because they don't have those, they don't have the orbital, even though it's neutral. It has only six electrons on the carbon. The carbon needs orbital. So it's very, very electron deficiency. And looking for electron very strong. And so what happens is it will grab any electron available. Grab electron from the carbon's H bond, grab electron from carbon bond. In the last reaction, you see what happens is actually this organometallic compound reaction with double bond. So how can you, some scientists find out, instead of like produce the carbene from the diazomethane, you use light, and they use some compounds that have those R group only, or some Cl group only, make this carbene more stable. Not really carbene because it's a carbene noise. carbenoid like molecules onto the double bond and produce cyclic structures. The reason for those kind of species, instead of simple carbene, you have a simple carbene, you have carbon, 2 electrons, and you have H. So this is our carbene. Electron deficiency, 6 electrons. Okay? So any of those species not stable, you are reacting with any available electron source, maybe from a chemical bond, maybe for a double bond, maybe from a single bond. So you want to stabilize that structure by, you can think about adding those CD3. CD3 can hyperconjugate. Or better use some of those like acetylenic, use chlorine. Chlorine has long pairs. So then you can think about how you prepare that. Well, you can really prepare those kind of carbenoid, for example, from this chloroform. The chloroform has 1 carbon, 3 Cl, 1 H. And we use some of those base hydroxide, sodium hydroxide, and you will take the H away. Then this carbon anion lost the Cl1 negative, and you produce this carbenoid. Now this carbenoid is not simply that, so this structure here is not our usual carbene. The carbene has only 2 H, and this carbenoid, so that can keep this much less reactive, because the contribution from Cl makes the electron deficiency. Carbon has a little more electron. And so then your result is very similar. So you can see, you can take this one with double bond, produce a 3-member ring, and a similar result. You will see the region specificities. And let's see one example. One example here, you start with a cis double bond. You take this one, you take the chloroform with some of those strong base palladium hydroxide, you produce a 3-member ring like that. And your final structure, that CLC, that little structure there, and 2 Cl on 2 sides. Okay, any questions? I think one of the homework questions is about this. So when you see those kind of reagents, you will produce a 3 carbon ring, and make sure you keep the stereochemistry from the double bond. next metal you will see is the copper. So the organocopper reagent is sort of the Gilman reagent. Gilman is a scientist was at University of Iowa, I think, and he worked there for many years. And I think since his 60s he become like blind, but then he do most of the work with the help of his wife. And, so he created one of those reagents, and so he started with some of those like the organolesion, and with the carbon halide, and change into alkyl copper. So then another organolesion produces the lithium dialkyl cuprate. So this reagent is very useful to produce a new carbon-carbon bond. And now you review so those lithium and magnesium. Right? So those lithium, organolithium compound can reacting with aldehyde ketone give alcohol. Green yard has magnesium that can also give alcohol. Then we see that zinc. And especially zinc is produces a three-member carbon ring, and now this copper. Okay? The copper will give you a new carbon-carbon bond, and not that like important like the organolithium or the green yard, because that can not only add in the carbon bond, also creating those alcohol. Okay? So, but still useful. Sometimes you want to just increase the carbon numbers. But it lost some of those alkyls. So you can kind of those waste. Okay? And you will see this the reaction will take the copper, the cuprate, the alkyl cuprate, and reacting with some of those halide, and it works best with methyl primary halide works best. Alkyl halide, vanillic and aryl halide, but there's some problem with those secondary and tertiary alkyl halide. But if you use that, and you can see some of those elimination reactions. So this reaction works best with methyl halide. It's best with methyl halide. Or some of the primary. Primary like this. So this gives two, that is X. So this one is methyl halide. Methyl halide and primary halide. Then tell you is also some of those vanillic halide. Vanillic halide like this. So this is vanillic. Aryl halide, so this is aryl. So this four is the best halide you use on those on the cuprate. We now see here are two examples. So one example, you take that the lithium dimethyl cuprate with one idle decay. And so that's halide, primary halide, primary alpha halide. And so when those metal from the metal cuprate replace I, and you can see you increase your carbon chain by 1 carbon. Okay. The second example, similar. Here you have 2 of those butyl. So the 2 of those butyl, you want to use 1 to replace I. And on the side of the bending, you have 4 just normal butyl. So you have butyl bending. Okay. It's very simple. And you can just increase the carbon numbers. Now the next example that means you are going to use the vanilla halide. So here you have vanilla bromide and reacting with this lithium diethyl cuprate, and you will add or replace this Br by an acid. It also reduce specific, which means the stereochemistry of the double bond is retained. See here, the stereochemistry of here, the double bond is E, or trans configurations. Your products still have the trans. Double bond still have the trans. This last example is aryl cuprate. So you probably have a benzene or naphthalene. The benzene here, 2 benzene. And you will use my benzene and replace this I, and increase the carbon numbers like that. This example of reagent, I think that's just when you see the copper bonding to like 2 of those alkyls, is a Gilman reagent. You will see there is a counter ion Li, because the carbon here is 1 plus. And you can imagine the 2 alkyl or 2 aryl are 2 negative. So you still have like 1 positive ion, like Li1 plus somewhere. So you remember this reaction is actually take 1 of those maybe the alkyl or vanilla or aryl. I'm going to replace the halogens in your molecule. So our halogen molecular is right here. Okay, now let's see how we add this on. Initially, this Cl is on this side. You need to keep the stereochemistry. Therefore, the Cl you add on to the alkyl or vanilla should be on this side. Right? And this stereochemistry also kept. Right? This stereochemistry here. This metal, this copper is trans, and you take the copper away, adding this on here, and this start coming here, double bond here, so also trans.
Is that the double bond between the O and the underneath?
Between,
Yeah.
yeah, here, double
It's
bond.
another double bond.
Right. It looks like this reaction in the Gilman reagent is a simple SN2. If that is true, then it will not make sense this SN2 can also happen on the veneer or on the aerial. The veneer and the aerial bending ring or double bond is not good for the SN2. They have a lot of electron blocking the attack of the SN2 or the nuclear fire, right? Because the nuclear fire has a negative charge. If you come closer to somewhere that also have a lot of electron, that will repel you away. Okay, so actually there are some of those characteristics of oxidation reduction of metals. So you can imagine that for example, dimethyl cuprate. Okay, so this two methyl group produce the bond with the copper and produce this anion. Then the halide add on produces complex intermediate. It's not simply like what the Grignard or the organolithium do. If this organolithium without that part, then this can be a very good nucleophile and SN2 attack this R and kick the X out. So what really have some of those characteristics, or still have those SN2 characteristics in it. And you take this anion, which bring out what you get from the Gilman reagent, plus the halide. So you did not really kick out the X completely in one step. You kind of take this in and just adding this both R and X onto the copper. Now this step, when you are seeing some data structures, when we talk about some other catalysts and happen very common, so some scientists propose this magnesium step for the oxidative addition.
What do you mean by some of the catalysts?
Huh?
What do you mean by some of the catalysts?
Some of the other catalysts?
Yeah, you just said that.
Yeah, there's the catalysts like those Palladium catalysts, and I think probably in this chapter did some other sections, and you will see similar mechanism, and you have the sort of the oxidative addition and reductive eliminations.
How so?
Okay. So the reductive elimination is starting from this one, and you will take some of those copper, like this one and this one away, and you will end up these two together and produce our products. You adding carbon and carbon, you adding a carbon and carbon bond. So the overall reaction for this mechanism looks like you start with R2CuO1A ion, which pretty much one side from the Gilman reagent. Oxidative addition produces intermediate, and then reductive elimination and combine the carbon-carbon bond. Yeah, there are some other transition metals like palladium and platinum. They have empty those t orbitals, so therefore they can coordinate with those ligand or ligand. And we attracting those aeroperos and halide nearby, and so then we will have a better chance to the bomb getting closer, the electron getting closer, so we can produce a new bond between some of those ligands. So those mechanisms still very, very actively studied.
What do you mean by ligand?
This is the ligand. So those are the this problem is use the ratio synthetic approach to devise the synthesis process of each of the following from indicating materials. Right. So you want to get this one from this. Let's say this is benzene. So we have this chain on the side of the benzene, and you want to get that from this. Right? So what you do is the best choice should be cutting which bond in this kind. Which bond should be cut? Think about use the carbon. Pretty much you can see you need to increase the bond here, increase the carbon number of carbon. And here you have how many carbon? 1, 2, 3 carbon on the side. And 1, 2, 3, you have 2 more carbon. Okay. So probably you want to cut the bond here. Yeah, so let's try that. So you want to cut this carbon here. And we learned this new technique to add a carbon-carbon bond by use the Gilman reagent and some of the halide. And then works good with like the aeroperal primary aeroperal halide, methyl, aryl, or veneer. So I think what you can do is let's use diethyl lithium diethyl cuprate. So we will probably will CH3, CH2, and 2 of that, and then you have the Cu, then you have the Li. Right? That means you need to somehow prepare this. Somehow prepare this BR. Then that's, if you remember that free radical reaction, then that's easy, right? So you are starting from this one, and use like the use like BR2 and peroxide. Yeah,
So secondary, the one right there,
which one?
first one to the left.
Not the peroxide here. This one is the peroxide. Right? Peroxide. Yeah. So now let's see the. Yeah, so now let's see what we really use. We will use this compound and use HBr and peroxide. Okay, any questions?
So we're gonna have our test on quiz on chapter 13 and then take home quiz tomorrow.
Yeah.
We can't have a take home quiz at chapter 13.
We probably can, but yeah, we will just take home. No,
We'll save half an hour in class. We'll save half an hour in class.
I did not
We
say.
can study.
I did not say that.
But we can go through lecture notes, it'll be so helpful. Trust me. Come on, please. It'll be like nice. We can ask you more questions. I'll ask you questions in class.
We can do. I know we can do like 2 at one time. But let's do like 1 at one time, right? So we can.
Or we can do that, yeah. But like that way, wouldn't that give us more time to ask the questions in class, cover lecture, more info?
Yeah, that's.
Because like if we take half an hour to take the quiz, then that's taking time away from lecture.
Okay, good. So gradually, gradually I want to become my professor I saw before. So maybe next time, the next few days, I will give you the quiz and you take it home and then come back. You show me your work. So let's do a flip.
What?
Do a class flip.
You do the quiz.
You do the quiz. You do the quiz. I will sit down.
I feel like that way you can like actually learn more, because that helps me. So don't you guys agree like class? No? Take home quiz for chapter 13, right? Well, give us some time. It's not funny, like, come on guys.
We all agree with you.
Give us more time though.
Okay, what's the question?
I was gonna say, like, instead of doing a quiz, you could make it like we had the quiz, like realistic. It's more like a worksheet, and then you could walk through the problems with us.
Yeah.
So that.
Yeah, that's what I said. So maybe I will give you the quiz for this one. So that's why I said we want to keep what we said. We'll take a visual quiz. Take the quiz of February 13 tomorrow, and I'll give you the quiz of February 14 like tomorrow. Take it home, right? Is that right? Okay. So then, for the next few quiz, I will try to make the lecture even shorter, and I will give the quiz earlier, and you can have you produce a group, let's say 4-person group, right? You start the quiz, then you are presenting your result.
Oh, I like that idea.
Like that?
Yes.
Can we just do it as a class?
Yeah, let's do that as a class.
You get them right.
So it's like we're teaching each other.
You teach yourself. You teach yourself.
Yes.
That's just should be, because especially you are sophomore or juniors, and the professor is only the facilitator. You still have to read the books and do the.
Yeah, that way you learn better. See, like, if someone knows something you don't know, they can correct you and teach you. Right, class?
Right.
Right.
So we're going to do the quiz like for that chapter the same day, like with like groups, is that what you're saying? Or the next day in groups? So that way we know the material.
Well, I will give you the quiz like 1 day before, 2 days before,
Okay.
and then you do the quiz like in a group. Whether you really do the group or not, it depends on you. But when you come back, you will give me the result in group, and then I will decide, you do all the questions, usually I will have 7 questions, 8 questions, and then I will randomly say, you group will give me the answer for the first question, and then you group will give me the question for the second question. Then everybody will say here, okay, was that he did it right or wrong, and I will give him some points. Right?
And then from now on,
Let's talk about
they're
the
basically
exams.
take home.
He comes and comes.
Can we please, please, you should take a look at our exams, they're not gonna be so bad. We need these points.
Let's do one more question on 13. Okay,
Let's go.
so everyone, let's just start from 13. I think we have about 27 people, and you can just, all 27. So just 4 person a group, right? 4 person, so 7 group are about 28. So one group maybe 20 is 3%, okay? So that's perfect. I usually have like 7 questions. If I have 8 questions, and I'm freely like volunteer who want to do like 2 questions. Otherwise, each group 1 question. Okay? Some questions little difficult, some questions little like easier. And yeah.
Okay, so then we're gonna do them in groups, and then we're gonna go over the whole quiz over with the class, and then turn them in.
Yeah.
Okay.
Your whole group of 4 people come here. Obviously, you want to get away with how you present the result. Yeah, I will use your right draw. I think we have 2 boards. And if we have still time, we usually have a lot of boards, but we can just, maybe we can have 4 groups come together presenting 4 questions, and then we'll have another 4, so that we will have still time. Right? Probably that will take about 20 minutes. But each group can have 10 minutes presenting the result. Then you will do that right or wrong, then the other group will come back. Yeah, about 20 minutes. And then that's good.
But I
Good
would
time?
So we're doing this with 13. We're gonna drive on here. We're starting on. Are we starting for tomorrow? Trial. Trial. Yeah, I'm gonna go.
13?
13.
13?
That's what trial we're doing.
And then we should have a take-home quiz too, like group take exam too. Cause like when I took my
All right. I think that's right. So that means your lecture will be quadruple the speed, and maybe 6 times the speed. You do very quick. I will just show you briefly something, and then you will just study, right? I will presenting all the lecture notes. Lecture notes, this version, the version you saw before, I have to blank. So let's try that. Try that.
Wait, can you repeat that? I needed that.
What can I say?
This seems like a solid plan. Let's just stick with this.
That means
We're gonna trial 13, and we'll see how this goes. We'll take it from there.
yeah.
you might have to start or continue.
So are we only getting 13 today?
Are we still?
Yeah, we get 13 today, and then we come back tomorrow and do this in class, and then you can.
Yeah, that's our plan. So we still taking the quiz tomorrow for Chapter-14 in the class. And I will, what?
13.
I thought you're saying we'll get 13 today, we'll do it, and then come back tomorrow, do it as a class, and then you'll give us 14, then we'll come back Monday, do it as a class.
Is that the,
I like
Yeah.
that.
Because we need to look count things through the lecture so we can solve problems and then present them.
So no quiz in class tomorrow. No. So we're done with the quiz.
Okay. We get them before class, right? Get them the day before.
That's a change.
It's a big change, though.
And we'll learn a lot too, so that's nice.
Better grades.
Better grades.
Better
And
teacher,
I'll
better
Makes you look better.
I love
You won't have to, you won't have to grade them anymore though.
So then the last
Compared to hundreds.
I think one homework problem having the last question, last session on me is about few scientists' name. It's very new, what kind of new? I think that was so this work was performed in the 1780s, and one name called the Heck. There's two reagent names, very Heck and Hill.
Was that a joke? You're making a joke.
So this Heck reagent using some of those very good, like those transition metal catalysts. And so what you can see is using the transition metal catalyst, you just use like the halide and the double bond. You don't really have to use like those halide with Gilman reagent or some other reagent. So when you will produce a bond. You can see this reagent, you produce the bond. Between this sp2 and this benzene. Okay. Also, one interesting rule, like what we know, like the so-called orbital rule, similarly apply to the transition metals. So transition metal, because it has those d orbitals, and we know d orbital can take 10 electrons. We have the orbital rule is from the s and t orbitals. So you can see this kind of so-called 18 electron rules, and you can use that and to like figure out those complex and which one is more reactive and get some of those understanding. So if you count those transition metals and see if they are unsaturated, and that means they have less than 18 electrons, and then you can take more ligand. Right? You can think about you can use them to like sort of the oxidative additions. Okay, another example is a homogeneous catalytic hydrogenation. It's a very unique catalyst, and usually you see the double bond. Okay? Let's see what we our conclusion. The Zeisel's rule. Okay? Zeisel's rule. The double bond with more substitution on it is more stable. Right? So the more stable one, usually in that chapter when we studied the alkene, which those compound has double bond, with the stable one will have the reaction goes easier. Okay? I think that concept sometimes may be a little confusing. So why the stable one can go faster? Which one goes faster depends on the activation energy. Right? So if you have a double bond, a double bond like this, okay, and compare with the double bond, have 4 substitutions like that. Okay? And this one is more stable. More stable. Okay? You want to use the energy diagram, if you see the energy goes up, if you want to use energy diagram, you can think about you have like monosubstituted is something like, or disubstituted like this. So this energy here, see this is energy here. Okay? Now this is for this line. And if you have a tetrasubstituted, so then your energy is here. Okay? And you want to make this reaction go like and climb over some barriers. It seems the unstable one will help the reaction easier. So this one is more stable. More stable, that means if this axis goes up, high energy, I use this line as lower place, that means this guy have a lower energy. Lower energy, that means you climb over the hill, you probably take more energy. This is only one variable. Okay?